Okay, so I'm going to finish up the very last part of the last talk, which I didn't have time to finish last time. So remember what we did last time. We were doing a separation result, where I wanted to show that here are two tasks, one of which can solve the other, but the other one, there's a model of computation where it doesn't go the other direction. So what I showed last time was that if we can solve this Mobius task, then we can solve a weak symmetry breaking. And what we showed is that if you can do the Mobius task, you can't do set agreement because this is a manifold and the Sperner's lemma argument holds. So now what I want to do is to show that if you can solve the anonymous version of set agreement, then you can solve weak symmetry breaking. And this is going to look a little bit different from what we've done before because this is actually an algorithm. So this is not a topology. This is an extremely simple algorithm, but it is worth understanding because it does something interesting. So what I want to show is that if we can do the anonymous version of set agreement, then we can do weak symmetry breaking. Now remember, weak symmetry breaking has to be anonymous because we want to rule out trivial solutions. And so set agreement does not have to be anonymous, but we can make it anonymous using techniques I'm not going to talk about. But I'm going to assume that we have an anonymous set agreement box that we can use. So we have n+1 processes that come in to the algorithm. And then we take our anonymous n set agreement object. That is, we lose one input. And they go into here. And then they come out. And when you come out, you write your ID, that is what the result of your anonymous set agreement, into a shared memory where everyone can see it. So you choose a value, you basically announce it to the world, saying this is the value that I got from my anonymous set agreement. Then you read everyone else's IDs. So I write the value I got, I read everyone else's. Then I say, well, did somebody write my ID out there? And either I see it or I don't see it. So if I see it, then I join group 0. Remember, weak symmetry breaking says that everybody has to join either 0 or 1. And if all n+1 participate, then somebody has to decide 0 and somebody has to decide 1. And we don't care what happens if there are fewer than n+1 participants. If I don't see my ID written, then I'm going to join group 1. So what I claim is that this is a way of solving weak symmetry breaking using only read-write memory and this anonymous n-set agreement box. So that means that n-set agreement is at least as strong as weak symmetry breaking because I can transform any solution for one into a solution of the other with just a little bit of memory on the side. So here's a kind of a proof outline. So if all of them participate, then the first ID that gets written, that process will see it and it will join group 0. So somebody joins a group 0. But because this is n-set agreement for n+1 processes, some ID is not going to be chosen by anyone. And that process is not going to see its ID written out. So it's going to join the group 1. That's it. So that's the reduction from anonymous n-set agreement to weak symmetry breaking.
So, yeah, why anonymous?
Oh, we want the whole protocol to be anonymous.
Okay.
And so that's why we want, if this were not anonymous, then we couldn't argue that the whole protocol was anonymous. So we're assuming that the black box that we have is anonymous. Now, I'm not going to prove this, but in fact, you can take any set agreement protocol and transform it into an anonymous protocol by doing some pre-processing.
But you take your ID as your value. So.
Well, you take, when you join the n-set agreement protocol, your ID is your value.
Okay. So
And what's anonymous about it is that if I permute the IDs, if I permute the inputs, then I permute the outputs. That's what anonymous means. So I can't say, oh, my built-in, my serial number is a prime number, and then do something different. So that's anonymous just means symmetric. under permutation of process IDs. Okay, so so the second part, the conclusion here is that some tasks are harder than others. You know, there's a kind of a, if not a hierarchy, then at least a directed acyclic graph of tasks. And I showed you that n-set agreement solves weak symmetry breaking, but not vice versa. So that's an example of a separation. So later on, we'll see other separation examples that are you know, sort of more interesting, but I wanted to do this one because it uses all the manifold properties that we spent time proving. The other thing that's worth pointing out is that this is a combination of both combinatorial arguments, you know, Sperner's lemma arguing about simplexes, complexes, topology, and so on, and an actual algorithm. And so you can see that these two approaches complement each other in this field. That is, anybody who tells you I can do everything using only algorithms is exaggerating, and anyone who says they can do everything combinatorially is probably exaggerating as well. And so combinatorial approaches are good for showing what we can't do. The same way that classical topology is good for showing that two spaces are not homeomorphic. It's more awkward to use it to show what you can do. We'll see some examples of algorithms that are constructed in topological ways, but they tend to be existence proofs rather than explicit constructions. But here, I gave you an explicit algorithm to show you that you can do something. And this is a pattern that you see in the field quite often. Okay, so now we're going to move on to the next.
Is that a non-disclosure slide?
No, it says it's a disclosure slide. So it says that it's licensed under Creative Commons, so you can do anything you want with it. You know, because otherwise I get tired of answering emails from people saying I want to, you know, use your slides. So it says you can do anything except make money. And if you can figure out a way to make money with this, then more power to you. Okay, so basically what we did in the last time was we showed you how to use Sperner's lemma to show that k-set agreement is impossible when your protocol complex is a manifold. So Sperner's lemma only works for manifolds. And so we looked at this immediate snapshot model where all of the protocol complexes are manifolds. And you know, we got separation results, impossibility, and things like that. Now, unfortunately, the real world is a cruel place. And it turns out that most of the models of interest, the protocol complexes are not manifolds. So we're going to need more powerful techniques to talk about those. But we're going to use the same tools that we use with manifolds, only in a slightly more sophisticated way. So this is a roadmap. So what I'm going to do is I'm going to give you proof of, I'm going to give you a general topological property that says that consensus is impossible in a particular model or for a particular protocol. Then I'm going to give you a specific application to read-write models to show that in read-write models this theorem applies. Then I'm going to go over and do the same thing, only now for k-set agreement. And I'm going to give you a general topological property and application to read-write models. And part of the fun of this exercise is that all of the mathematics in this course is provided in a just-in-time manner. So I'm going to define new mathematical machinery right before we use it. This is partly because I don't know what I'm going to be covering yet. So it's convenient to introduce things as they go along. But it also highlights sort of what exactly you need to know for each result. So I'm going to introduce some fun concepts along the way. So first thing I'm going to do now is give you a general theorem that tells you when you cannot solve consensus. So we'll take a simplicial complex. This is not a smooth surface. This is a complex, but I get tired of drawing all the edges. And the path is defined, but you take a vertex, you take an edge to another vertex, you take a vertex and an edge like that. So sometimes this is called an edge path, but we'll just call this a path. And we'll say that
you can't go to the same vertex twice.
you can. So we actually we won't ever do that, but in principle, it doesn't have to be a simple path. Later on, we'll actually introduce loops, but for now, you've got a starting vertex, an ending vertex, and it could be non-simple. It could intersect itself and do all that stuff. It won't matter for anything that we want to do here. So all we want to say here is that a simplex is path connected if I can take any two vertexes and link them with the path.
Use your Gmail because this is getting more and more private.
Oh, it's usually only a spam.
Well, I don't mind.
Well, no, I don't want to distract people from the. Okay, so your path connected if any two vertexes can be linked by a path. This is the familiar notion of connectivity you see in graphs and so on. So the theorem says, the general theorem about when you can and can't do consensus says that if for every n simplex, every global state that has everybody as a state, if your protocol complex is path connected, that is, in executions where no process fails, all of the possible states are connected to each other by a path. And then in executions where one process can fail, that is, where you have an n-1 simplex, the protocol complex is non-empty. So if nobody fails, then your complex is path connected. If one process fails, then you can still your protocol will still terminate. So basically, this says in all executions that tolerate one failure. If that's true, then you can't solve consensus with that protocol. So the ability to solve consensus is connected to path connectivity. And the interesting thing about this theorem, at least from my point of view, is that it doesn't say anything about what kind of communication mechanism you're using. It doesn't say this is true in shared memory. It doesn't say it's true in message passing. It just says that whatever your communication model is, if the result is a path-connected simplicial complex, then this holds. It doesn't say anything about the timing model. It doesn't say anything about the scheduler. So again, all of these model-specific things go into reasoning about the protocol complex itself, but once you have the protocol complex, all you need to do is test to see whether it's path-connected, and then you can answer the question, does this solve a consensus? So this is an example of another example where we can take all the model-specific things and push them into a corner and use this general theorem that applies to every model. And the only thing you need is you have to be able to tolerate one failure for this result to hold. Okay, so here is a kind of proof outline. So I'm going to, the proof works for arbitrary number of processes, but I'm going to show it here as if there were 3 processes, just to make the pictures look concrete. But the pictures are not the proof. The pictures are just there to suggest what's going on. So here is the protocol complex if all the processes run. Here is the protocol complex if R fails and only P and Q run. So you see one is contained in the other. So without loss of generality, let's assume that P wins in this particular execution. Somebody's got to win, so let's say it's P. It obviously can't be R because R didn't participate. Let's do the same over here and look at the protocol complex where Q and R take steps, but P fails. And then without loss of generality, R is the winner. How do we know that these exist? Well, one of our hypotheses was that if all but one run, then the protocol complex is non-empty. So because each of these is non-empty, we know that there's at least one vertex in there, and that vertex must have a color. And we can pick different colors here.
So this is ID consensus, so you decide on the identity of a single process?
No, this is,
Or binary consensus?
no, this could be any kind of a consensus at all. And so this is colored with the winner, which is the ID of the process that proposed the value that won. We can assume that the values are all unique.
Okay, so that's ID consensus.
Yeah, it could be ID consensus, but technically it could be any kind of a consensus where the value.
It has less meaning if you look at binary consensus.
Oh, yeah. Well, I mean, it works for binary consensus too. Because what we're going to do is our other hypothesis, right, was that the protocol complex itself was path connected. So it says we can find this, take this vertex where blue was decided, and we can take this vertex where red was decided, and we can construct a path we can find a path between them. And what do we know about paths where we have one color here and one color there? Well, basically, it's any edge. There's got to be some edge along here that has two colors. This is not exactly one-dimensional Schwerner's lemma, because there could be more than two colors in there. But it's the same idea. You can't get from red to blue without switching from blue to red somewhere along the line.
If you have n processes, then this is each running n minus 1, and 1 is the winner. One of them is the winner.
Yeah. And so there might be n processes. So this edge here might be a face. Yeah, here we have two processors, but it could be a face of a higher dimensional simplex. But each n simplex here represents the final state of the protocol, and the color represents the winner. So this edge here represents an execution where there were two different winners. But consensus says you can only have one winner. So that's a contradiction. So that says that if your protocol complex is path connected in the absence of failures and non-empty in the presence of a single failure, then you can't solve consensus. And this is actually, if you look at kind of classical operational proofs of this, like the famous FLP proof, this structure is kind of there, but it's implicit, because they're talking about unfolding executions in time and so on. But if you think of it statically, then it's just drawing this picture. Okay, so now I've given you kind of an abstract property that works on any model of computation. Now I want to argue, well, this actually works for wait-free read-write memory, because that's one of the more interesting applications. So I'm going to show that consensus is impossible in wait-free read-write memory by showing you that it satisfies the hypotheses of the theorem. And therefore, we can apply this general theorem to this specific model. So we need to show that for every n simplex, the protocol complex is path connected, so that if you run without any failures, that the set of possibilities is path connected. And then I need to show if there's a single failure that the protocol, somebody still terminates. A single failure doesn't cause your protocol to fail. So in order to do this, we want to kind of argue inductively. So we want to argue about the path connectivity of big simplexes in terms of the path connectivity of its components. So we want to break the big protocol complex down into smaller pieces, argue inductively about the smaller pieces, and then be able to put the argument together at the higher level. So the interesting thing about path connectivity is we know that if each component is path connected, so here we have a bunch of components, and each one of them is individually path connected, and each of their pairwise intersections is non-empty, then what can we deduce? So each piece is path connected, their pairwise intersections are non-empty. We we can deduce that the whole thing is path connected. The union is path connected. So this is a pattern that we'll use for more sophisticated properties later on, where we talk about each component has some property, the intersections have a slightly weaker property, and then we can put everything together to say the union now has this property. So we'll be doing this in a much more complicated way later on. Okay, now here's an important concept that we'll use in a number of proofs, and that is think about, I'm running this protocol, and each time the scheduler allows you to take a step, the number of reachable final states shrinks. So when you start out, it's like your first day of college, all things are possible. Every final state is reachable, but every time you make a choice, that rules out certain final states. So every time a process takes a step, the part of the protocol complex that is reachable at that point, the set of final states that can happen, is smaller. Until finally, when the protocol finishes, the state that you're in is the final state, and that's the only possible final state. So you can think of it this way, is that if this is the reachable complex and the scheduler says process A takes a step, then only a fraction of the protocol complex is now reachable. On the other hand, if the scheduler had allowed B to take a step, then a different piece of the protocol complex would now be reachable. So when associated with taking steps, we can identify subcomplexes of the final protocol complex. So you can think of it, so weight-free computations are finite trees. You take a finite number of steps and then you stop. There's no loops or anything. So we could, here, for example, is all the possible states for a weight-free computation where each process takes 2 steps, and there are 2 processes. So initially, again, the entire protocol complex is reachable. At the end, only a single simplex is reachable, which is the one you've actually reached. And then let's say a property is eventual if it's satisfied by individual simplexes. And this could be any property you like, as long as it's well-defined. Now suppose it doesn't hold at the start. So we have a property that's false at the beginning of the execution, but always becomes true at the end. Now, let's define the state to be critical if the property that we're interested in is false, but any further step will make it become true. So this state is a critical state for the red property, because even though it's not true here, no matter who goes first, no matter who goes next, that property will become true. So I claim that every weight-free property, every property that is always true at the end and false at the beginning, has a critical state. That there's no way to devise a protocol that doesn't have such a thing. And the way to see it is fairly simple. We start out in a state that doesn't satisfy it. And imagine you're the adversary scheduler that wants to waste as much time as possible. And so every time you have a choice between, if red goes, then we end up in a state that satisfies. If this process goes, then the property becomes true. If this process goes, we postpone it. So we postpone it. And then we do it again. Given a choice, we always pick the path that doesn't make the property become true. And so the claim is that eventually, because we can't run forever, if we could run forever, this wouldn't be a weight-free protocol, we must come to a state where no matter who the scheduler lets run, red becomes true. And that's the critical state. So we're going to focus our arguments about what exactly happens at this critical state. So what I really want to show is that the property of interest was really true the entire time. So I'm going to assume by way of contradiction that it was false. I'm going to allow the adversary scheduler to move you into a critical state. And then we're going to take out our microscope and look at this critical state and say, what could possibly be happening here? And then we'll show that there's a contradiction in this definition. And from this, it was the case that the property that we're interested in was true all the time. Okay, so what I've shown so far is you start out in a state where it's not true. There are critical states where the property is henceforth true. So in particular, if I want to show that a... Yeah?
Could there be a situation where the property holds one child, it doesn't hold one child, it doesn't hold, and then it holds in another child?
Oh, yeah, you certainly have a situation where here it holds and here it does not hold. But I'm not saying that every state is critical, but only that there are critical states and that a scheduler can always maneuver you into a critical state. And so then, but then we'll show that critical states don't exist, and therefore the property must have been true the entire time. So let's assume by way of contradiction that the read-write protocol complex is not path connected. Now in the end, the reachable complex is a single simplex, which is clearly path connected. So the property of being path connected has a critical state. So there's some state where the reachable complex is not path connected, but no matter who goes next, the reachable complex will be path connected. So it looks kind of like this. Here we have our C is our critical state. P of C is the protocol complex. And if P goes first, then we have this subcomplex. Q goes first, we have this subcomplex. And R goes first, we have that subcomplex. So basically what we're doing is we're taking the reachable complex from the critical state and we're chopping it up into 3 small pieces. And what do we know? Well, we know that these are what's called the covering for the protocol complex. You know, the protocol complex is the union of these 3 complexes. We know that P of C is not path connected by hypothesis because it's a critical state. And we know that each of the elements of the covering, each P sub I, is path connected, again, because this is a critical state by hypothesis. And so what I'm going to show now is that there's a contradiction hiding in here, that it can't be the case that each of these things is path connected, and yet their union is not path connected. And to do this, we need to look a little bit more closely at what's going on. In particular, I'll show you that each pairwise intersection is non-empty. And that's by our observation implies that the whole thing is path connected. That contradicts our assumption that it's not path connected. Therefore, it must have been path connected from the very beginning. And for some of you, this may seem like a fairly elementary argument, but I'm going through it in detail because we're going to do it again for higher dimensional notions of connectivity, where your intuition may not be quite as good. So I want to go over this slowly and in detail so that when we do it again in higher dimensions, you'll have some intuition about what's going on. Okay, so basically I want to show that each pairwise intersection is non-empty. So what is the interpretation of this? Well, this is the reachable complex if P goes first. This is the reachable complex if Q goes first. So how could a view be in the intersection of both P going first and Q going first? Well, it's some execution where the process can't tell who went first. So you look at your view and you say, well, it's possible that P went first and it's possible that Q went first, but I can't tell from what I've seen which of these 2 things happened. So that's the operational definition of what it means to be in the intersection of these things. So we're going to be looking at what could P and Q be doing in this critical state. So remember, we're talking about read-write memory. By read here, I think of it as atomic snapshot. Think of the memory as having multiple reader, single writer variables to make things fairly simple. All of these models are computationally equivalent. You can simulate anyone with any other one. And so what they could be doing is, well, P could be reading and Q could be writing. They could be reading the same thing. They could be reading different things. You know, this is the case analysis of all the possible interactions they could be having. So here Q is about to read. So consider the execution which Q doesn't read, and P wakes up and it runs all the way through and finishes its protocol. Now consider the alternative where Q goes first and it reads the value, and then it goes down to the beach here and hangs out for the rest of the computation. And then P wakes up and runs to completion. And what happens is that P sees the exact same thing in both of these executions, which means that the view that P had in both cases is the same, which means that they're the same vertex. So this vertex, because it's in the execution where P went first and it's in the execution where Q went first, is in the intersection. So we made a lot of progress. So I've shown you that if anybody reads, it couldn't be the case that anybody reads in this critical state. So next possibility is they could be writing distinct variables. So there's one execution where P goes first, it writes X. Q then writes Y, and P runs by itself, and then it halts with the view. We could do it the other way around, and P runs by itself. And what happens is that, again, these things look exactly the same to P. So it's the same vertex, and that vertex has to lie in the intersection. So there you are. So we're narrowing things down. We only have two cases left where they're reading and writing where they're both writing the same variable.
You assume that writing is commutative?
No, writing to...
The memory doesn't remember in what...
Oh, yeah. Yeah, if the memory did know what order, then things would be different, but that would be a different model. And in fact, when you start talking about other models of computation, like test and set and compare and swap and all of these atomic things that memories actually do provide, then things will be different. So this result really depends on the semantics of read and write memory. If you change those, then this result will also change. So this is the model-specific reasoning that I mentioned. So here, what happens? Well, P could write X, and then it runs by itself. Then it halts. OK, Q writes that Y. P immediately obliterates that by overwriting it, and then it runs to completion.
Q writes X.
X, oh, that's right. The person who's keeping track of bugs, please note this. Thank you.
X and Y pointers or values?
Values.
So they write on the same variable?
Yeah, so this is a typo. This should be X. So I want Q to write X, and then P immediately overwrites it. So nobody can tell that that was written. Variables don't remember any history. And so, again, this is really depends on the semantics of read and write memory. So same thing, PC is the same in each case. So the intersection is not empty. So we've shown that there's a contradiction. There must be a critical state. We looked at the critical state. The critical state doesn't make any sense. Therefore, there can't be a critical state. Therefore, it must have been path connected the entire time. And so our assumption that we started out in a state that was not path connected is disproved. So that's the proof by contradiction. OK, so what that says is that if you want to show that consensus is impossible, you need to show two things: that in the absence of failures, your complex is path connected, and in the presence of a single failure, your protocol still somebody halts. Those are the only two things you need to show that consensus is impossible. And if you want to apply this to other models, then you go over and you do the same kind of reasoning we did here. You just need to show that in your particular model, with your particular memory model, communication model, failure model, that these two completely combinatorial properties hold. What are we doing on time?
5 minutes past.
OK, so I'll go a little bit further before we take a break. OK, so now I'm going to do the same thing for case set agreement. So we did consensus, which says that everybody has to agree on one value. Now we're going to weaken it and say, well, OK, if you want to agree on no more than a k distinct values, that's OK. And that should be easier somehow. It should be more fault tolerant, it should be faster, it should be possible, all these good things. So what we're going to do is we're going to follow the same pattern that we use for consensus, where we showed that it was a topological property of a protocol complex. And then we applied the result to wait-free read-write memory as an example. So we're going to do the same pattern where I'm going to give you a general abstract combinatorial property and then show that it applies to read-write memory. So the core to understanding consensus was this notion of path connectivity. Now, I want to revisit path connectivity and think about it in a slightly different way. So one way to think about path connectivity is as a map of spheres. Now, degenerate spheres. So here, think of these 2 points, the endpoints, as a zero-dimensional sphere. So the 2 points that are equally far from the center. And what I'm doing when I say that there's a path between them, it says that if I take this map of the zero sphere, I can extend it to a continuous map of the one-dimensional disk. So I'm moving from discrete to continuous here. This is, we're going to start edging into continuous mathematics now. So one way to think about path connectivity is to say, well, I've got a map from a zero-dimensional sphere can be filled into a one-dimensional disk. And you can think of the process of taking a map of a sphere and filling it in to a disk as filling in a hole, or maybe showing that there is no hole there. So by showing that something is path connected, you're really saying there's no zero-dimensional hole there, where we interpret that as meaning being disconnected. So, we'll call this property, we'll say a complex is zero-connected if I can take any map from the zero sphere and extend it to the one disk. Again, now we're talking continuous maps. So we can generalize this to higher dimensions. So here I have a map of the one sphere into this complex, and I can extend it to a map of the one disk. If I can do that, then we'll say that this is one-connected. So this is one-connected because it turns out that every map of one sphere can be extended to a one disk. So that means another way to think about that is if I take an elastic band and put it in the complex, I can contract it to a point. That's another useful way to think of this. There are all kinds of different ways of doing this. Beg pardon?
The disk should be called, I think, two disks.
Oh, yeah. Did I say one disk?
Yeah.
Oh, well, yeah. That's another bug. Thank you. Yeah, that's a two disk. Now, here's an example of something that is not one connected. So here's a torus. I have a map of a sphere, but intuitively you can see that there's no way to fill this in here because there's a hole there. And that hole acts as a kind of obstruction to filling in the map. So when you think of something that is not connected in some dimension, that means there's a hole there or something blocking it. We can take this higher, and here we have a two disk. It's filled with air, and we can map that into a complex, and we can fill that in to a solid disk and continue the maps, and then that's two connected. And so we can sort of go on up into any dimension that you like. So here's the actual definition. So we'll say that a complex is n connected if for every m less than or equal to n, any continuous map of the sphere, I'll explain this notation later on, into the complex can be extended to a map of the next higher dimension, the n+1 disk. So that's just writing in letters the pictures that I showed you before. And it turns out this notion of connectivity in higher dimensions is exactly what you need to understand case-set agreement in the general case. As an aside, we'll say -1 connected is non-empty. So we'll have lots of formulas where we talk about connectivity, and we'll say that something is -1 connected when we say it's non-empty. Okay, so here is the big theorem for case-set agreement. It says if we start out with every n simplex. The protocol complex, when there are no failures, is k minus 1 connected. If there's one failure, the protocol complex is k minus 2 connected. And then when we go down, when we get to n minus k simplexes after k failures, we want that the protocol complex is minus 1 connected. Could you mark a formatting bug on tech point must have fallen asleep or something. So this only makes sense when you have, for protocols that tolerate k failures. So we have these k conditions which basically say that you start out being k minus 1 connected, and as the dimension of the simplex drops, so does your level of connectivity. And then at the bottom, we demand that it's only a non-empty. And you can see this is a direct generalization of our consensus requirement, where we said that we said that if there's one failure, if k equals 1, then we want to be non-empty, and we're 0 connected in the absence of failures. So when you set k equals 1, this is exactly the condition that we had before. So now we're going to prove this. Yeah, so this is, yeah, so if this happens, then you can't solve a k-set agreement. So, so you notice that I've snuck in some continuous mathematics here. And some of you may be feeling a little uncomfortable because, really we've only defined complexes in combinatorial terms. Never mind the pictures. I told you that a simplex is a set, a complex is a set of simplexes, which is a set of sets. And I haven't said anything about continuity, metric spaces, or anything. And so now what I need to do is kind of go back and fill that in and tell you what I mean when I talk about complexes in terms of geometric objects and not just combinatorial objects. So almost everything we've done so far we can explain in purely combinatorial terms, but now we're going to start using mechanisms that will require some geometry and point set topology and things like that. It's all elementary, but we have to define what it means. So as I mentioned, each simplex is a set, each complex is a set of sets, and that's worked fine so far. But instead, we need to give this a geometric interpretation, because we're going to need to borrow results from other branches of mathematics. So we'll say that a vertex is just a point in some sufficiently high dimensional Euclidean space. So everything happens in finite dimensional Euclidean space. We'll say a geometric simplex is the convex hull of a set of n plus 1 simplexes in general position, affinely independent. So we often will switch back and forth between combinatorial and geometric, and books do this all the time. And after a while, you don't notice it anymore. But really, this is a point set. This is 2 points in the edge between them. This is a solid triangle, and so on. So these are things with geometric meaning. A simplicial complex is basically an embedding of all of its simplexes in Euclidean space, with the property that every pair of simplexes intersect either in another simplex or not at all. So you can't have, say, two triangles that sort of meet in a messy way. They can meet along edges or at points in a nice, clean way, but they can't be all mushed up together. I think in Hebrew, the technical word is tzimis. It can't be a tzimis. So the notation that I used before, we'll say the polyhedron of a complex, which we'll put in this line, is the point set occupied by the geometric complex. And sometimes we'll get lazy, we won't put that in because it's clear from context, but we'll use it at the beginning just to emphasize the distinction. Now, a key notion that we're going to be using a lot is the idea of a subdivision. So informally, a subdivision, you take a simplex or complex, and you chop it up into smaller ones. And so geometrically, it's still the same point set. It's just that we replaced one big simplex here with lots of small ones. And we kind of implicitly did that when we talked about earlier on about manifolds. But now we're going to do this in a more systematic way. So what is a subdivision? Well, a complex B is a subdivision of A if for every simplex B of beta, there's a simplex of A so that the point set of A alpha lies inside of the point set of beta. And for each simplex alpha of A, the geometric realization of alpha is the union of a finite set of polyhedrons of simplexes of beta. So the picture that you saw says everything you really need to know. These definitions are here just to make it unambiguous. You know, if you look at the picture, you really understand what's going on here. Okay, one particular subdivision that we'll be using a lot is called the barycentric subdivision. And we're going to go over this one in detail because I'm going to give you a kind of formal combinatorial definition and an informal geometric definition. So this is what it looks like. So informally, what you do is you take the barycenter, the centroid of each of the simplexes of all the dimensions, and you link them together like this. So this is the barycenter of all three. This is the barycenter of these two, and each individual vertex is its own barycenter. So combinatorially, what we'll say is that each vertex of the barycenter corresponds to a face of the original simplex. And particularly, so this vertex here corresponds to itself. A face, remember, is just a simplex of lower dimension. So each of these corners corresponds to itself. This new vertex here corresponds to this edge. So each vertex, this vertex corresponds to the simplex of which it is the barycenter geometrically. But combinatorially, it's just a set of faces of sigma. And then I'll give you the rule for turning them into complexes. And so then here, this is the entire triangle corresponds to this vertex. A simplex of a barycentric subdivision is just a set of faces ordered by inclusion. So you take the faces of the simplex have a obvious partial order based on inclusion. You take all the chains of faces ordered by inclusion, and those are simplexes of the barycentric subdivision. So combinatorially, the barycentric subdivision is you take the partial order of faces, you look at all the chains of ascending faces, and each one corresponds to a simplex of the barycentric. But you can also just think of it as looking like this, if you like a geometric interpretation. But what I want to emphasize is that even though we'll be drawing pictures like this every time we talk about barycentric, you don't need to use any geometry to define it. You will need to use geometry if you want to prove that this is a subdivision. We're not going to do that because it's kind of tedious and long, but you know, you'll have to accept on faith that the barycentric subdivision really is a subdivision, given the definition that I've given you here. Okay, the other tool we need are what's called barycentric coordinates. So I want to, given a geometric simplex here, I want to be able to refer to the points in its polyhedron. And standard way to do that is that we can give it by barycentric coordinates, where I take each of the vertices, V0, V1, and V2, and I give them a coefficient, T0, T1, T2, with the property that the coefficients all lie within 0 and 1, and they all sum to 1. So it's a stochastic vector, even though this has nothing to do with probability. And every point of the polyhedron of a complex has a unique representation using barycentric coordinates, because you take different vertices. So you tell me which in this case, 3 vertices, and what the 3 barycentric coordinates are, that's a unique representation for every point in the polyhedron. And if you wanted to prove that something was a subdivision, this is the tool that you would use to do that. Okay, so we'd like to go back and forth between kind of combinatorial stuff and continuous stuff. Because sometimes there's a perfect continuous theorem that does what we want, but what we really care about ultimately is this combinatorial stuff, because we're really interested in computation at the end. So we'd like to move back and forth between combinatorial and continuous things in a nice way. So imagine that we have a simplicial map. Remember, a simplicial map is a map from vertexes to vertexes that also carries simplexes to simplexes. It's sort of, I'm sure there's a word for this in category theory, but it's a basic morphism that we care about. Then down here we have continuous maps from point set occupied by A to the point set occupied by B. And so, you know, I'll use this sort of absolute value notation when I want to represent something that's geometric. And so one direction, if you give it a simplicial map, it's easy to turn that into a continuous map. And the answer is we just use the barycentric coordinates. So if I give you a simplicial map, I can you know, wave my magic wand and turn that into a piecewise linear continuous map. And you know, you can do it 5 times before breakfast because it's so easy. The other direction is going to be harder. So what we really want to do now is we would like to go from continuous to simplicial. And so here we need to open the garage doors and roll out a little bit of machinery because we're going to need something called the simplicial approximation theorem. Now, I'm not going to prove the simplicial approximation theorem because it's a standard theorem you can find in any textbook. But I'm going to spend a little bit of time explaining what it is and what its implications are because we're going to need it in several places. So it's a very handy tool to solve a number of our problems, and I want to make sure that everyone understands what it is. What's the time?
Time for a break.
Okay, so you can take a break and refresh yourselves, and then I'll come back and